The toggle clamp is subjected to a force F at the handle. So that's the handle of the toggle clamp, subjected to this vertical force F at this handle. That's the handle. So determine the vertical clamping force acting at E. Okay, so the question is asking us to determine this vertical clamping force at E. So that's the vertical clamping force at E. So the toggle clamps, to describe what a toggle clamp is, I want to share with you a YouTube video, a very short YouTube video. So just watch it. Okay, you see the action? Okay, so let's try to see once again. So you have this red handle here, and then this clamp here, clamping item here, let's say. So you apply force on the red handle, push it down, and then you clamp it. You clamp a material, you hold a material, like squeeze a material. So that's the idea of a toggle clamp. So okay, as for the solution, and okay, realizing that there is a link element here, CD. So that link element CD is pinned at both ends, and so we can easily realize that that's so link element, link member CD is a two-force member. So two-force member. So solution of such problems becomes easier once we realize that there is a two-force member within the system. Okay, because it gets easier to find the unknown reactions within a free body diagram. So we're going to start by drawing a free body diagram of the handle itself and separating the link element from the handle. So member B, C, and then at this point we have a force applied here. So free body diagram, free body diagram for the handle here. So we have this handle here. Okay. Right, so we have an applied force F here, and we have at a distance 1.5 A. Okay, and we have a distance here A over 2, and at this distance we have we have a pin here, that's pin C, and we have another pin here. So at point B there's a pin, and at point C there's a pin. So at point B we have two support reactions here, BX. So at point B we have here BX, and that's BY. And at point C, at 30-degree angle, we have an applied force here. Through the link CD, we have an applied force of FCD, that two-force member. And this angle is 30 degree. Okay. So anything else that we need to write here? Okay, we have this distance. This is not a very good drawing, I guess, but let's assume that this is A over 2. Okay, so that A over 2, that A over 2 seems to be unequal, but let's assume that that is the case. Okay, so on this free body diagram, we're going to be writing moment equilibrium around point B to find FCD. So that's 0. Okay, so we have FCD, so two components of FCD, vertical horizontal component and vertical component of FCD. And so as for the vertical component, that's FCD times cosine 30 degree, so that's that, and A over 2 is the perpendicular distance to point B. Okay, so we have for the horizontal component, so that's sine 30, and the perpendicular distance, the lever arm, if you like, A over 2, and we have the force F and times 2A equals 0, so that gives us FCD equals 10.93 F. Okay, that's a function of F. Right. Okay, so for so equation for Bx, we can write sum of the forces in the x direction is equal to 0. So we're gonna have Bx minus FCD times sine 30. So FCD is 10.93 F times sine 30 degree equals 0. So Bx will be equal to 5.464 F. Okay. So we are asked to find, let's remember what we are trying to find eventually. We are asked to find the vertical clamping force at E. Okay? So we have found Bx here, and we're going to continue now. So let's go ahead and write a free body diagram for this piece here that I am now hatching, this piece here. Okay, so let's draw a free body diagram for this piece, including this one as well. Okay, so this particular part here. So the free body diagram for that part is kind of, we have this here going up and then something like that going down, something like that, and then we have this part here. Okay, and we have okay, that piece. This is a bolt here, okay, with threads, some threads on it. Okay, so essentially we have this reaction force, vertical clamping force actually, Fe is what we are trying to find. Okay, so this, what is this? So we have point A, we have point B. So just recently we found Bx equals 5.464 F, and we have point A here. Okay, so this distance between Fe and point A is equals 1.5A. Okay, and this distance is A. Okay, and right. So if we write equilibrium equation here, so moment equilibrium equation, moment A is equal to 0, point A equal to 0, we are essentially excluding the effect of By here. We could have found By, but we didn't do that because I'm about to now write an moment equilibrium equation around point A, and By is excluded from that equation. Okay, you can see that the line of action of By is passing straight through point A, so that's outside the equation. So we are left with Bx and Fe. Okay, so this moment equation will give me 5.464 F. So that's Bx times A. Okay, times A, and minus Fe times 1.5 A. That's equal to 0, and we find for Fe 3.64 F. So that's the clamping force Fe written in terms of F. So if F is 10 kilonewton, then that'll be Fe will be 36.4 kilonewton. Okay, so that's Fe is 3.64 times F. Okay, it'll be 3.64 times greater than F. So that is the solution of this particular problem. Thanks for listening.